Hello everyone, welcome back to quarter number 2 of this semester, and the first topic that we're going to discuss in this quarter is about Newton's law of motion. For information of everybody, Newton's law of motion was formulated by Sir Isaac Newton. And if you want to know the history of law of motion, of how Sir Isaac Newton's created or formulated laws of motion, you can read the history in internet. But my task for this lesson is to discuss to you the 3 laws of motion. Okay, now let's proceed to the first law of motion. The first law of motion is also known as law of inertia, and this states that a body at rest will remain at rest and a body in motion will remain in motion unless acted upon by an external force. So for example, assume that we have this box, and this box is being placed on the top of the table. So looking at this diagram, there are 2 forces acted on this diagram or on this example. The first force is the downward force or the force of gravity, and we can draw that like this. So given the symbol of F sub g, or force of gravity, and the second force is the upward force. And this upward force is the normal force. So if we're going to get the net force of these 2 forces, this will be given as F sub g minus F sub n. Now take note that whatever the value of the downward force, the normal force is also equals to that. In simple word, the net force of this one is 0. That is why, according to law of inertia, the body at rest will remain at rest unless it is acted by an external force. So in this case, the box will remain at rest unless acted by an external force. And if we're going to apply a certain force on this box will move in a constant velocity unless it is again acted by a certain external force, so that this box will stop. So if there is no force or external force acted on this moving box, the box will continuously moving in a constant velocity. So that's the concept of law of inertia. And I just want you to know that inertia is referring to the mass of an object. In other words, inertia is the natural tendency of an object to remain at rest or in motion at a constant speed along a straight line. The mass of an object is a quantitative measure of inertia. So if you have a bicycle and a train, and if you are going to compare the inertia of these 2 objects, obviously the train has a greater inertia than the bicycle. So the higher the mass of the object, the higher the value of inertia, and that's the bottom line of first law of motion. Let's go for second law of motion. Second law of motion is also known as law of acceleration. This states that if a net external force acts on a body, the body accelerates and the direction of the acceleration is the same as the direction of the net force. So if the object acted by a net force or an external force, the acceleration or the direction of the force will be the direction of the acceleration. So for example, we have here a box again, or yes, a box with a certain mass, and this is acted by a force, and the direction of the acceleration will be the direction of the force. So whatever the direction of the force, that would be the direction of the acceleration. So if the force is towards right, or towards let us say towards east, the direction of the acceleration is also towards east. So in this case, the force, or mathematically the force, is given by force is equals to mass times acceleration, in which acceleration is directly proportional to force. That means the higher the amount of force applied to the object, the higher the amount of acceleration. And in terms of mass, acceleration is inversely proportional to its mass. That means that the higher the value of mass, the lower the acceleration of a certain object. So in this expression, we have really remember or recall this one, because this is the foundation of the second law of motion. Whatever the situation, when you ask about Newton's law of motion, particularly application of second law of motion, you have to recall or remember this formula: F is equals to mass times acceleration, because this is just a simple a concept of explaining Newton's law of motion, wherein the m here is the mass of an object, and a there is the acceleration, and F is the force or net force or external force. So the SI unit for mass is kilograms, SI unit for acceleration is meters per second squared, and SI unit for force is Newton, or big letter N in symbol. And take note that Newton is equals to kilograms times meters per second squared. Let's go to sample problem for second law of motion. Anyway, this one is just a basic principles of second law of motion, but we're going to discuss this one in a deeper concept as we finish discussing the third law of motion, the application of second law of motion, because second law of motion is very wide and we cannot discuss that in detail in this video. We have to make it in a separate video lesson. Okay, now let's go to sample problem. This is still in second law of motion. Assume that we have 3.5 kilograms of papaya, and this is pushed across a table. If the acceleration of the papaya is 2.2 meters per second squared to the left, what is the net external force exerted on the papaya? If you have a module, we have there an explanation, or shall we say solution to this problem, but I think I have to explain it for the sake of your understanding. So first one is we have to list the given value that we have. So the given value in this problem is obviously we have mass of 3.5 kilograms of papaya, and we have also acceleration of 2.2 meters per second squared to the left, and we are tasked to find the external force exerted on the papaya. So applying this formula, or we can also create a free body diagram of this one so that we can visualize what is happening. So let us say this is a table, and we have here a papaya, and this papaya is being acted by a certain force, which is this is unknown force, and the papaya accelerates to the left with a value of 2.2 meters per second squared, and this papaya has a mass of 3.5 kilograms. So what is the external force acted on that papaya to accelerate with a value of 2.2 meters per second squared to the left? So solution for that, we just recall the general formula of second law of motion, which is given by F is equals to mass times acceleration, and all we need to do here is to just to supply or just to plug in the given value that we have in this problem. So the next one is to substitute all the given value that we can find in this sample problem. So the first value or given value here is the mass of the papaya, which is 3.5 kilograms, and the acceleration of the papaya, which is 2.2 meters per second squared. So 3.5 times 2.2 meters per second squared is equals to 7.7 newtons to the left. Or we can also rewrite this one as negative 7.7 newtons, and this will be our net external force. So the answer for that is it can be this one, or if you want to express this word here as a sign, so we can use this expression here. In other words, I can also write the answer as 7.7 newtons to the left. So it's just the same with this answer here. Okay, now moving on to the third law of motion. The third law of motion is also known as the law of interaction. This concept or this law is very applicable particularly in sending rockets or rocket space science. They're using the concept of law of interaction to be able to send rockets into the space mission. Okay, but I will not discuss about sending rockets to the outer space. Our focus now is just to define and just to give you a simple understanding of what is really a law of interaction is. So law of interaction is this states that when two bodies interact, they exert forces on each other that at each instant are equal in magnitude and opposite in direction. Meaning to say, we have two forces, but these two forces are just be equal. But the bottom line here is third law of motion is the application or the application of two forces, which is action and the reaction force. So for example, we have this box here. Like for example, this box has a mass of something, and this is let us say this is a surface of the table. Let us assume that this is table, this one is the box. So when you place a box on the surface of the table or on the top of the table, as I mentioned in first law of motion, there are two forces acting on that object or on that box. The first force is the downward force, or in first law of motion we call this one as a force of gravity. But now since we are in third law of motion, we're going to call this one as action force. So action force. Now this action force can be weight, which is weight is given by mass times gravity or acceleration due to gravity, and this weight is just be equals to force or action force. So whatever the force or the value of force exerted the value of action force in this diagram, that would be equal to the upward force or the normal force in first law of motion. But in this case, since we are in third law, we will call this one as reaction force. Reaction force. So in reaction force, whatever the value of action force, that would be automatically equals to the reaction force. That means mathematically the action force is equals to reaction force, in which F is equals to mass times acceleration. That means that action force is equals to mass times sub A times A sub A to represent that we're referring to action force, and for reaction force this is F sub R, or just be equals to mass times sub R times acceleration times sub R. Or we can also rewrite this formula as M sub A times A sub A is equals to M sub R times A sub R, and this equation here is the equation for law of interaction, wherein M is mass A is acceleration, and also so as to that. So you always remember that equation. The foundation of this formula or this equation is actually the formula for in second law of motion. So you always remember the formula or general equation in second law of motion when dealing with Newton's law of motion, because when you come with a certain problems, yes, or certain situation that requires understanding or application of Newton's law of motion, you can simply apply the basic principles of Newton's law of motion by recalling this equation here, which is the equation for second law of motion. Okay, so this is the equation for law of interaction. Whatever the force in the action force, that would also be equals to the reaction force or the upward force acted on that particular object. So let's try to examine this sample problem here. Suppose that mass of a spacecraft is 11,000 kilograms and that the mass of astronaut is 92 kilograms. In addition, assume that the astronaut exerts a force of 36 newtons on the spacecraft. Find the acceleration of the spacecraft and the astronaut. So the first step that we're going to do here is to identify given value that can be found in the problem. So the given value are mass of spacecraft is equals to 11,000 kilograms, which is this one, and mass of astronaut is 92 kilograms, and we have the force exerted by an astronaut, which is equivalent to 36 newton. That is why we have this given value here. And after that, we're going to identify what are the unknown values. So at the unknown value here, we are tasked to find the acceleration of spacecraft and astronaut. So this one. Now solution for that, we're going to solve first for the, let us make some free body diagram so that we can simply visualize what is happening in this problem. So assume that this is a spacecraft and this one is the astronaut. Let us say this one is the astronaut. Astronaut has a mass of equivalent to 92 kilograms, and spacecraft has a mass of 11 kilograms. And astronaut exert a force, that means the astronaut push the spacecraft with a value of 36 newtons in force. So the spacecraft has a acceleration which is unknown, and we can assume that this is directed towards east, and this is positive value, and the acceleration, which is the reaction force, since the action force is being applied to the spaceship, and the reaction force of the spaceship is directed towards east, and the action force now of this astronaut is directed towards west, and this is the acceleration of the astronaut, and this one is the acceleration of the spacecraft. And we can simply assume that the acceleration of the astronaut is negative and the acceleration of the spacecraft is positive. So first thing to do is to solve for solution. Let's solve for acceleration, although we listed the acceleration of spacecraft, but we can reverse the process. We can compute first the acceleration of the astronaut, or vice versa. So solve for the acceleration of the astronaut. So the acceleration can be solved using again the general equation of the Newton's law of motion, which is the second law of motion, which is force is equals to mass times acceleration, and this is equals to force of astronaut equals mass sub a, just to indicate that we're referring to the astronaut value, and this is the acceleration of the astronaut. So cross multiply, divide both sides of the equation by m. So this will be cancelled out. So the remaining variable here is a. So a sub a is equals to f sub a over m sub a. So we are now tasked to find the equation, or I mean the acceleration of the astronaut, which is now in this form. So we can substitute the available value that we have here. So the force of astronaut is 36 newtons, and the mass of astronaut is 92 kilograms. So this is equals to 36 newtons divided by 92 kilograms is equals to negative 0.39 meters per second squared. Why? Because newtons is equals to kilogram times meter per second squared, and this one divided by kilograms. So you cancel out kilogram to kilogram, so the remaining unit is meter per second squared. That is why the unit for acceleration here is meter per second squared. So the answer, the acceleration of astronaut is equals to negative 0.39 meters per second squared. Okay, now let's go to the acceleration of spacecraft. Solve for acceleration of spacecraft. So F is equals to mass times acceleration, and this is equals to F sub S is equals to M sub S, A sub S. So since in third law of motion, we said that the force or the action force is equals to the reaction force, we will assume that the force of astronaut here is just be equals to the force of the spacecraft. That means the force of astronaut here, which is given by this value here, the 36 newtons here, 36 newtons, can be used to also describe the value, or yes, to substitute as value for the force of spacecraft. So meaning to say the force of astronaut here is just be equals to the force of spacecraft, which is 36 newtons. In that case, we will use the 36 newtons value here to substitute for the variable F sub S here. So this is 36 newtons equals the mass of spacecraft is 11,000 kilograms. So this is 11,000 kilograms times A. So divide both sides of the equation by 11,000 kilograms, and this is 11,000 kilograms. Cancel out, cancel out. So the remaining variable is A. So this is A is equals to 36 newtons divided by 11,000 kilograms. So you divide this one, 36 newtons divided by 11,000 kilograms, and this is equals to 3.27 times 10 raised to negative 3 meters per second squared. I just explained the value or the unit for acceleration, or it can be written as 0.003. You round off this one into that, so 0.0033 meters per second squared. So the acceleration of the spacecraft is equals to 0.0033 meters per second squared. So the answer for this problem is for the acceleration of spacecraft is this one. Okay, so if you have some clarifications regarding this lesson, you can directly go to our group chat and type your questions there. Now for your assignment, try to pause the video and read the statement here and do the required task. Once again, this is Maz, your physics teacher. Happy New Year, and see you in the next video.